Okay, welcome people. This is the very first pre-seminar of 2026. And speaker is Ben Bouwen, who's a local here in Prague. And he's going to talk about groupoids, graphs, and C-star algebras. Please.
Thank you for the introduction. And thank you for getting me to give this nice little pre-seminar here. I think the title "Up to Permutation" is what I wrote, what I gave as my title for this talk. So the main focus is going to be giving you a very gentle, not extremely rigorous, but mostly relying on intuition, introduction to groupoids and their corresponding C-star algebras. Now, as I said, I will be not everything I say will be entirely accurate. I will sweep some adjectives under the rug and do so hopefully knowingly at most points, but I'm sure if anything, there are a couple of experts here in the room who will be able to correct me if I'm wrong. But yeah, so for those who do not know what a groupoid is, let me just get started by, well, there are a couple of definitions one can make. Some might think the following definition is already very illuminating. So a groupoid can be defined as a small category where every arrow is invertible. Okay, now that's a definition, but it doesn't, especially if you're not really a category theorist, it doesn't tell you very much about what's really going on. So the way I want to present groupoids to you is the following. So let's draw this small category here. It's for now this shape. And so the point is we have a number of objects in this category, and then we have some morphisms going between them, say gamma alpha, and the point is that every morphism is invertible, so in the sense that there always exists some gamma inverse. And really what you should be thinking about as being the groupoid are the morphisms. So we identify, for example, this object as the morphism gamma inverse. And as such, the objects we will denote as G0. So these are the this is what we will call the unit space. Why it's called as such, I'll illuminate a bit in a moment. And there are two other important objects that, or not objects, two other maps that I want to define, the range and the source map. So you can define the source map of a morphism gamma as simply, well, the object that it's coming from. So as I said, in this case, that will be gamma inverse gamma. So reading from right to left, I guess. And then the range will be gamma inverse. And so the point is, and the reason that, reason that this is called a groupoid is because really what is going on is it's kind of like a group, except you can't compose every single element with every other element. Only if the range of the second corresponds is equal to the the range of the first is equal to the source of the second, then you can compose things, and so on and so forth. So this, for example, this would then be alpha gamma. So if you will, alternatively, a groupoid is a group, except not every pair of elements of the group is composable, only a specific subset of them. And this is also okay. Maybe first let me say the main point of interest from especially from a Caesar algebraic perspective for groupoids is we also want to equip them with a certain topology. So endowing them with a topology and as such calling them topological groupoids. So we want a topology such that the unit space is Hausdorff and the composition whenever it makes sense, and the range and source maps are continuous. All right. So, yes. Yes. Well, for our purposes, yes, I guess, because, but I guess theoretically it could, yeah. But I don't know if the construction of a groupoid Caesar algebra even makes sense if the unit space is not a set. Right. So examples. As I alluded to earlier, groups are indeed also groupoids, where the unit space is simply a single object being the units, and all of the group elements are arrows from and to the same unit. So G, H, and so on. Then I guess the other extreme of, and okay, I guess I should say topological groups, because I presume that there's also some topology on there. And then the other extreme would be topological spaces. In the following sense, well, the unit space is just the topological space itself, and there are no arrows anywhere.
You need an above each point.
Yes. Yeah. Exactly. Yeah. No non-trivial arrows, let's say. All right. And so this is already kind of quite nice because this structure of a topological groupoid can capture both groups and topological spaces, both of which are of interest to Caesar algebras, for example, because both of them have been used in the past to construct Caesar algebras out of them. And so, as we will further see, groupoids can also be used to construct Caesar algebras, and they will correspond to the original constructions for group and group Caesar algebras and the obvious continuous functions on the topological space in the case that the groupoid is of that form. All right, then maybe one slightly less quote unquote trivial example. Okay. So matrix groupoids. Here, we consider the following set. So we just take the first n natural numbers squared, and the unit space of this groupoids will be the tuples with the same number in both entries. And then maybe already the name matrix groupoids might suggest what kind of composition you can define on this set, namely, you only allow pairs to be composable when the second entry of the first equals the first entry of the second, and then you define this as getting rid of the second, or getting rid of the j here and just remaining with this. And so this is already quite reminiscent of how the matrix units inside the n by n matrices act. And in fact, as it will turn out, this will, the corresponding C-star algebra will be the n by n matrices. All right. Then one more example. And this now, we get to the second part of my title, what I'll call the path groupoid. So this is constructed from a graph. So given a directed graph, E with vertex set E0 and edge set 1. And let's, for now, assume that so for every vertex, there are finitely many and non-zero arrows coming into this vertex. And from such a graph, we can consider the set of paths which are infinite in one direction, in the sense that you start at a certain point in the graph and you just go on forever. So let me note that as such. So we just take x1, x2, so on, where we want all xi to be edges such that the range of 1 is the source of the next. Okay, and now how can we construct a groupoid out of this? Well, and one thing to note is that one can construct the following, consider the following map where we just forget about first entry of our path. So say this is our path, where this just denotes the different entries of our path, and we map this to the path which starts at the second edge. And now the path groupoid is defined as follows. So we take a tuple with 3 entries where x and y are paths, and which are such that after moving the path x, or getting rid of the first m entries of x and getting rid of the first n entries of y, they are the same path from that point on. So this is saying if we apply this shift map m times to x, then this is equal to applying the shift map n times to 1. So up to a finite part, these two paths should be the same in the tail end. Okay. And how do we construct a construct a composition out of this? Well, you can kind of already guess what the structure will be. So if we have two pairs or two tuples as such, we can compose them if the second entry or the last entry of the first is equal to the first entry of the second. And in that case, we define the composition as x k plus L. And you can, and it's pretty easy to see that this is again an element of this set because of the way it's defined. All right, and then the inverse of an element x, k, y is then y minus kx. And the unit space will be pairs x, 0, x. As such, and so this can naturally be seen as the path space itself. Okay. And now the reason that we are interested in these from a C-star algebraic perspective is in fact because we can construct a C-star algebra out of them. So remember For a C-star algebra, you need star algebra. You need it to have a norm under which it is complete, and you need the norm to satisfy the C-star identity. Those three things. Okay, so how can we construct a? Let's start with constructing a star algebra out of this. That seems like a first nice step to do, and well, it's not so hard to find one under some additional conditions on the groupoid, which I will not mention. But if we take a look at the compactly supported functions, continuous functions on the groupoid, so to the complex numbers, so continuous and compactly supported. And these are sort of well behaved enough to where we can define well pointwise addition and scalar multiplication, and then the product that we want to define on this is a convolution product. So this is a generalization of, or it's very much in analogy with what one does to construct a groupoid C-star algebra, namely, you look at two compactly supported functions, you define their convolution product at a point gamma within your groupoid to be the sum of all overall pairs alpha and beta of your groupoids, which combine to the gamma that you're given, and then you take f of alpha, g of beta. And the reason that this sum is well defined is because our functions will be compactly supported, essentially. Okay, and then finally, we need an involution. And this we can also just define pointwise as the complex conjugate of the inverse of the element gamma that you're given. All right.
This convolution product that you defined required to be italic.
Yes. Yeah. That's what I'm saying. Like there's some adjectives here that I'm sweeping under the rug, and in order to make the picture clear, there are some hidden assumptions underneath there. All right. And now we have a star algebra to complete it to a, well, there are, let's say, two canonical ways to complete it into a C-star algebra. Once again, in analogy with what happens for groupoids. So the first is the full groupoid C-star algebra. And this is defined as, or will be equal to the completion under let's say the maximal norm, where the norm of a function f space take the supremum over of I of f, where I is a star representation of CC of G. And there's a bit of work involved to check that this is well defined, and this in this construction, the natural map in constructing this natural map from CC of G into this completion is actually injective, but the main point is you're completing with sort of the largest possible norm that makes sense. And then the other one is reduced. And here one can, one instead completes by embedding CC of G in as a left regular representation over. So we take, say, x. We take, for each element of the unit space, we consider the L2 functions of the, let's say, well, the isotropy at point x, meaning all, one looks at all arrows which start and end in the point x. This is a group now, in fact, and one takes the direct sum of the bounded operators on this. This will embed into here, and then you just take the operator norm completion inside of here. Okay, so this is kind of, and if you've seen the construction of group C-star algebras, then this should be very familiar. And let me finish by saying or by confirming so for this construction, as I mentioned for groups, this gives you back the group C-star algebra as expected, or the reduced group C-star algebra, depending on which one of the two you take. For logical spaces, you'll just get back the, I guess, yeah, C0 functions on your logical space as expected, and then the matrix groupoids, CC of G, so CC of Rn will already be equal to the n by n matrices, and therefore this is a lemma that you can prove on your own time, maybe. And then any completion will, this is already a C-star algebra, so this will give you, regardless of which completion you take, just the n by n matrices. And then for the path groupoids, I don't have time to give you the definition, but I guess there was, so preceding the introduction of groupoids, I assume, already quite some time ago, people defined a C-star algebra associated to a directed graph. And I do not have time to go into the precise construction, but the point is it exists, and it is equal to the full, or is isomorphic to the groupoid C-star algebra of this path groupoid. All right. So yeah, I guess in summary, groupoids are nice because they capture lots of naturally occurring examples of algebraic objects or combinatorial objects, which have already in the past been used to construct C-star algebras out of them, and therefore are worth investigating by themselves. And Malcolm will tell you more about not just groupoid C-star algebras, but also graph C-star algebras, and in fact for higher rank graphs. So thank you for your attention.
Are there some questions or comments? Maybe I can start with one. So, is there some kind of way? So, let's say if you don't start with a groupoid, but maybe with a Lie algebroid to construct a C-star algebra, that this might be dual to this way here. I mean, there probably you need some smooth structures. I think it's not that interesting, but
I haven't heard of this, but maybe other people in the room.
Yeah, maybe people looking for Lie groupoids, but I don't know about going up the road.
Yeah.
Like, I didn't think about activity. I think have this paper on Lie et al. Groupoids, and from from them they construct some kind of algebra, non-commutative algebra of differential functions and things. But yeah, but what were you asking about? You were asking about Lie algebroids or something.
yes.
Okay.
Here you have some terms from groupoids, so maybe you have some universal enveloping algebra. The algebroid that is would be dual to this thing. I don't know.
Lie algebroids. Yeah.
If you take in your, quantum groups world, then your dual object is kind of like the group C-star algebra. So in some ways, this is the dual. The C-star algebra is the dual of the groupoid, I guess, in some sense. So maybe it is the Lie algebroid type thing.
Comments?
Maybe if we don't want to consider Lie algebroids right away as a construction for Lie algebras.
Probably whatever is known as will be contained within the paper that you mentioned from this Lie groupoid / algebroid construction. I don't think Yeah. Yeah, somehow the Lie groups, groupoids, algebroids don't really seem to pop up that much at the moment. Or at least, for now, we've been happy with just considering this class.
Give the idea, I mean, I don't know if this makes much sense, but the idea would be that Lie algebras are, you could say, are easier than Lie groups. So would be could be natural to think of if there's a similar way, just using the datum of a Lie algebra or a Lie algebroid rather than the groupoid or Lie group groupoid. This was the thought. Okay, some more questions? Maybe from online audience. So if you have a question, just unmute yourself and go for it. Okay, doesn't seem to be the case. Then let's thank Ben again. Now there's a short break and then there's the main seminar.